forget what the Mott variable is, relative to all these different variables dealing with weather, like temperature in January, precipitation, temperature in July. So then there are some demographics, the proportion of people over 65, the population size, the typical amount of education that they have in that district, etc. So it is a geographic data set, and these are different areas, and this is, you know, how polluted it is, how much rain they get, and then some socioeconomic stuff as well, right? And there are 60 observations from memory, 15 different variables. So it's quite a complex data set, right? And good luck looking at the correlation matrix and making sense of it, straight up, right? So fine, you can look at a correlation matrix if there's 2 or 3 or 4 or 5 or 7 data points, but soon it becomes, well, what the hell is going on here? How much redundancy have I got there? I mean, what I can see immediately is that there are some relatively high correlations going on between variables. So hopefully, I will be able to reduce this, because currently the data is sitting in 15-dimensional space, right? So I have 15 different variables. So if I was to plot it, each variable has a different axis, so it's sitting in some sort of funky 15-dimensional space, which doesn't do me a lot of good if I want to try and plot it. So that's the correlation matrix. That is going to be the input that we're going to use. This is what we actually deconstruct. We do an eigenvalue deconstruction of this correlation matrix. Okay? And when we do it, this is what we get. We get some big eigenvalues, right? So this is the first PCA axis. This is the second PCA axis, all the way down to the 15th. Right? And by the 15th axis, well, if I'm plotting my data in 15-dimensional space, of course I'm going to be able to explain everything, 100% of the data. Right? The first axis, even though it's been split into 15 axes, the first axis is always going to be the most important, right? It explains 30% of the variation in the data, 30.2%. The second axis is, remember, this is decreasing order. Second axis contains 18%. That means if I was to plot the data on PC1 and PC2, I have a representation, a map, that explains about 50%, 48% of the data, right? I'm losing about half of the information. But it's much better than just choosing 2 variables at random and probably losing a great deal more, right? You can see that, you know, as we go further and further down, right, the amount of variation, the importance of the axes gets smaller and smaller. So by the 14th and 15th, these are adding nothing, right? Very, very little information. We're hitting 99% pretty high up, or 98% way up here. The last 4 axes add combined less than 2% of the variability in the data, right? So really, actually, how many axes do we want? That's the big question, right? Well, for plotting purposes, the answer is 2, or maybe 3, right? But if we want to summarize the data really well, how much is enough? It's hard to say, right? If we use this idea of eigenvalues being bigger than 1, we would say, well, the first 5 eigenvalues are bigger than 1, right? So the first 5 axes are the most important one. After that, we're not really modeling anything, or the variation that we see could be due to chance. Right? That would be one way of looking at it. The first 5 eigenvalues explain around 80% of the variation. That's a rule of thumb. Some people try and choose, 80%, some number of axes that explains at least 80%. But in reality, it depends on your data. If you've got really noisy data and highly unstructured data, then you're going to need a lot of axes to try and account for it, right? Okay, so that's so far so good. Hopefully you understand that. These are the actual eigenvectors themselves. So what actually makes up an axis? Right? Remember when we have that 2D plot? This one here. That axis here is equal to some value times variable x1 plus some value times variable x2, right? It's a combination of these two. Right? This is the combination here. So this first eigenvector, principal components 1, prin1, is equal to minus 0.345479 times precision plus minus 0.065 times the average January temperature plus blah, 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 blah. Right? Every variable will have a particular weighting, a coefficient with it. Right? So those coefficients that are really, really small, very close to 0, let's see if we can find one here. Can we find a particular variable? Well, the January temperature, 0.06, right? That's pretty small. I think it's probably, and SO2, sulfur dioxide. Let's just go with the January temperature. This January temperature has a coefficient of negative 0.06, meaning it has very little influence on PC1, right? Whatever value of January temperature, it doesn't really affect PC1. It doesn't have a lot of weighting with PC1. So the first axis doesn't reflect January temperatures much at all, right? It is, however, reflected very heavily in the second axis. January temperatures has a score of the second axis has a score of 4.482. So that second axis, if the January temperature increases, then that value along that second axis is very high. Okay, so it's what they call the loadings. And in fact, I don't know if I've plotted these out. Oh no, I have not. As you go on later on, it'll take me too long to print it out. You can actually see, we'll print out PC1 and PC2. I'll do this shortly, and you can see the actual variables with respect to PC1 and PC2. They are projected onto it, right? And you can see that those variables that are a long way along. I'll stop now because I don't have the graphic. I'll just create the graphic, then I'll talk to you. Okay, but the second half of the lab, you can actually start to see which are the important variables. You're trying to put the map that you create into context with respect to the original variables. Okay, so I will produce this for you guys soon and then explain it to you.